All right, in this video, I'm going to show you how to find the inverse of a 2 by 2 matrix, okay? But before we can actually get to that, we need to discuss the concept of an identity matrix, okay? And if you recall, earlier in the course when we were talking about the real number system, we said that the number 0 was considered an additive identity. That's because any number added with 0 is itself. And then the number 1 is considered a multiplicative identity for all real numbers because any number multiplied by 1 is still itself, okay? So we kind of have the same concept for matrices, okay? So the identity matrices that I'm going to show you now, these would be considered the multiplicative identities for 2 by 2 and 3 by 3 matrices, okay? So the 2 by 2 identity matrix has the following makeup. The first row would be 1, 0, and the second row would be 0, 1. Okay. The 3 by 3 identity matrix, the first row would be 1, 0, 0. The second would be 0, 1, 0. And the third would be 0, 0, 1. So I think you can kind of see the pattern here. Think about what it would be like if you went out to a 4 by 4 identity matrix, okay? So what again we're saying here is that if I took any 2 by 2 matrix and I multiplied it by this guy, it's not going to change the elements in that first matrix. And any 3 by 3 matrix multiplied by this guy is not going to change the elements, okay? Now, consider when you multiply two matrices together, we can say that they are inverses of one another if their product is the identity matrix. So if I took a 2 by 2 matrix and I multiplied it by another 2 by 2 matrix and I got the identity matrix, I know that those are inverses of one another, okay? It's the same concept, with multiplicative inverses of real numbers. Let's say I have the number of 2/5. Well, its multiplicative inverse would be its reciprocal of 5/2. Those, of course, multiply to the multiplicative inverse or multiplicative identity of 1. Okay, so exact same idea that we can relate back to with real numbers. All right. Okay, so in our first example, we are given a pair of matrices and we want to determine whether or not they are inverses of each other. All I simply need to do is find their product, and if that product ends up being the identity matrix, I have inverses, okay? So if I try to find x times y, I know a 2 by 2 times a 2 by 2 is going to result in a 2 by 2. If I go with first row and first column elements, 3 times 1 added with -2 times 1 is going to give me 1. Okay. If I go with first row, second column elements, 3 times 2 added with -2 times 3 will give me 0. Okay. And then if I go with second row elements and first column elements, -1 times 1 added with 1 times 1 would give me 0. And finally, second row, second column elements, I'd end up with -1 times 2 added with 1 times 3. That's going to give me 1. So notice I am getting the identity matrix here. So it seems as though, yes, x and y are, in fact, inverses of each other. But recall, matrix multiplication, it's not commutative. All right, so we also need to check the other direction. We need to check, is the product of y and x the identity matrix? Okay, and just to speed things up here, I'll tell you, yes, in fact, they are. Ends up giving me the identity as well. So we are going to conclude that yes, x and y are inverses. Okay. All right, now what about with the second pair of matrices P and Q here. So let's go after the product PQ. Another 2 by 2. All right, so if I do first row and first column elements, 3 times 1 added with -1 times 2, that's going to give me 1. So we're starting off good. All right, move over to second column, so second row, second column, that's going to give me 3 times -3 added with -1 times 4. That will be -13. And right there is a red flag. Okay, I was expecting that to be a 0 for the position that it's in for the identity matrix. Okay, so the fact that this is not a 0 tells me that we can conclude P and Q are not inverses of one another. Okay, you don't even have to worry about finding the other two elements of that matrix. Okay, so now let's show you exactly how you can find the inverse of a 2 by 2 matrix. We'll give you a little formula that you can use. Okay, so let's say we're working with matrix A, and it has the following elements: A, B, C, D. Then the inverse of matrix A is represented with this notation. Okay, it looks like A to the negative first power, but that really represents a notation to talk about the inverse of A. And you would read it as the inverse of A or A inverse. Okay, so it's going to be equivalent to 1 over the product of AD subtracted by BC multiplied by the following matrix. Okay, D, negative B, negative C, and A. Okay, so a few things to kind of discuss about this formula. So first of all, the fraction out in front, so 1 over the product of AD subtracted by BC, you need to think of that as a scalar. That entire fraction is a scalar that would be multiplying the matrix to the right of it, okay? Secondly, I want you to notice, this should look familiar to you right here, that denominator is the determinant of the original matrix A that you're trying to find the inverse for, okay? And then notice the elements of the matrix that we're multiplying the scalar by. So basically what I've done is I've switched the position of these two terms, and then I've kept B and C where they're at, but I just like changed their sign, okay? So that's standard anytime you're trying to find the inverse of that matrix, okay? And then the last thing I'll draw your attention to is what's listed down in the bottom. We want to notice that if the value of the original matrix, the value of the determinant of the original matrix you're trying to find the inverse for, if that value is 0, then the matrix is not going to have an inverse, all right? And the reason for that is you would be taking 1 and dividing it by 0, which is undefined, okay? All right, so now let's put this at play with a couple examples. So notice the directions. Find the inverse of the matrix if it exists, okay? And we have to put that in there for the simple fact of if the determinant of the matrix is 0, we know that the inverse will not in fact exist, okay? So let's start with matrix R here. The determinant for matrix R would be the product of -1 and -2, which is 2, subtracted by the product of 0 and 8, which is 0. That's going to result in 2. So I know for a fact that R should have its inverse. All right, here's the notation for that inverse. It's going to equal 1 over that determinant of 2. We're going to multiply that by the following matrix. I'm going to have a -2 a 0, a -8, and a -1. And now I will simply multiply that scalar of 1/2 to each of the 4 elements of that matrix. So that's going to lead me to -1, 0, -4, and -1/2. And there's my inverse. Okay. All right, for matrix S, start by finding that determinant, which would be this product, -12, subtracted by this product, also -12. It's going to turn out to be 0. The fact that that is 0 means that the inverse for S does not exist. Okay, so what we're seeing here is that inverses can only be found for square matrices, okay, but not all square matrices have an inverse, okay. All right, now it's your turn. Go to practice 1, pause the video, work through that yourself, and then come back and check your work with mine.